Okay, while you are downloading and installing that software, if you haven't already, let's just go over a couple of announcements. The schedule is almost finished. You know, this is class 29 out of 30. So your final homework assignment is due on Thursday. You've already submitted the project, and I'm about halfway through grading those. I hope to finish them no later than Thursday. Today we're going to do just a quick, brief exposure to HEC-RAS. This program and more sophisticated open channel flow modeling is the subject easily of an entire semester at the graduate level. And I'm not particularly familiar with HEC-RAS. It's just within the last 1 or 2 semesters that I've actually learned how to use that in the basic way myself. But we'll kind of go through it together and see what we can do as far as working a similar example to one that we used one of the spreadsheets. So I do want to talk a little bit about the final exam before we dip into HEC-RAS. The final exam is scheduled for Thursday the 9th, and it'll be here in this classroom starting at 10:15 a.m. We'll have 2 hours. And so the coverage is comprehensive, but as I mentioned before, it's going to be kind of added emphasis on the more recent material. Now, I have made the decision that you don't need to come ready to solve any water gems problems. You're done solving water gems for me, for now anyway. The length of the exam, I intend to have the exam be about 1/3 longer. You know, just in terms of the number of questions or you know, the amount of work you can expect to do, but you're going to have quite a lot of extra time. And so, you know, the ratio to added length to added time is going to be more favorable for you. I hope that it'll feel less urgent and that you definitely won't feel crunched for time on the final exam. Do bring your computer with access to Excel and the ability to upload your solution to MU Online, so you're going to need internet access to do that. Equation sheet, I'm going to provide the same 4-page equation packet that you've had for your earlier exams, and in addition to that, you're allowed to bring 1 page of notes where you can fill on the front and back any equations that you feel like you need beyond those that are provided. Outlines of solution strategies, column titles if you want to kind of replicate things that you've done with Excel, or workflow for iterative problems where you're having to start with a guess and gradually converge on some solution. So just basically whatever you'd like for the equation sheet. And the weight is 20% of the course grade, so that's the same as both of the earlier midterm exams. Those were also weighted at 20% each. So it definitely has the potential to make a change to your overall grade. Okay, so that exam, 9 days away. Any questions about the final? No? All right, so as I mentioned, we're going to try and do just a really brief taste of HEC-RAS. How many people here have already used HEC-RAS in some capacity? A couple of you, maybe if you work at the core, I guess. Maybe you've seen it used. All right, so we're going to do the most basic thing that I could imagine, and that is solve a problem similar to this one, where we had a rectangular channel. And remember that when we were solving this with Excel, the initial things that we asked ourselves were, you know, for this channel that's described, and we have unsteady flow because of this weir, this broad-crested weir is in the channel, and that's causing a little bit of pooling upstream of the weir. What we were given was a measured depth just upstream of the weir, and we were given the flow rate that's going through that channel, and we knew the slope of this channel and its roughness. And so with the slope and the roughness and the geometry, of course, we can calculate the normal depth. And with the flow rate that's given and the flow conditions, the channel geometry specifically, we can calculate the critical depth. And so having done that, calculating the critical and the normal depth, then the first thing we did was classify the water surface profile type. Now remember that an M1 profile is talking about at a certain location. And so the certain location in question is just immediately upstream of that obstruction. We had a measured depth of 3.8. And so if y is greater than y sub n, and y sub n is greater than y sub c, that's an M1 profile. So if the normal depth is greater than critical, that tells you mild. If critical had been greater than the normal depth, then that would tell us that we have a steep slope. But in this case, it was a mild slope, and then the 1 means that the measured depth of 3.8 meters is deeper than either of these other two. So that puts the measured depth in zone 1, which is the highest of the three regions if you're dividing the flow up into the imaginary line, that's the critical depth, the imaginary line, that's the normal depth, and then our actual flow water surface. Now, in this procedure that we did, in the step-by-step method, we had to divide it up into segments, and the rule of thumb there was let's not have a segment where the elevation and depth, the water surface change is more than half a meter. But the reality is the more segments that we divide it up into, the greater the accuracy is going to be. Because what we're essentially going to be doing is we're going to be approximating the shape of this curve with a series of lines. And we're assuming that the water surface slope is linear between these segments. And so if we divide it up into lots of smaller slices, then it's more true that each curved segment approximates a line if you've got lots of those little, lots of the segments that are able to represent that curve more accurately. So we just went with 6 when we solved it initially. With HEC-RAS, it's going to be quite a lot easier for us to replicate cross sections and maybe get more accuracy because we're dividing it up into a lot more reaches. And so what we did was we calculated that from this measured location up to where it matches back up with the normal depth was about 2,430 meters. Now, as we'll find through this example, the actual length may be a bit longer when we divide it up into more than 6 segments. So we're going to be adapting this example. Once again, we're using the same 7-meter wide rectangular channel. And let's say that we have a 4-meter height that the water can be flowing through. If we think about this as like a rectangular trough that the water is going down and it's 4 meters tall on either side, but we don't necessarily know how deep is the water within that rectangular trough, except for at this one control point where we have a measured depth of 3.8. So this is going to be what we call a boundary condition. And the boundary condition is just a location where we have a fixed measured known value, and then we work towards the unknown starting with that given. Of course, the other things are going to stay the same, like the channel slope, the flow rate, the roughness. So all of that's going to stay constant. We're going to try and put that into HEC-RAS. Now, one of the tricky things in HEC-RAS is that the editor for defining what the channel geometry looks like, it's basically an XY coordinate system that we have to utilize. By the way, does somebody have a marker here today? I forgot to grab one as I left my office. I can always count on you to hook me up. You've got so many colors to choose from. Thank you very much. All right. So if we're going to be thinking about this rectangular channel, the things that we're going to be trying to find out is, first of all, in part A, if we go 1,500 meters upstream from the control point, how deep is the water? That's one thing that we're interested to find. And then the other is, how far do we have to go upstream until the water depth is within 1% of the normal depth? And we're saying that within 1% of the normal depth because if we said until it's exactly equal to the normal depth, because of the way that the numerical solver works, you almost never really get back to the normal depth. It's kind of like, you know, the conundrum of how long will it take you to walk to the wall if you just go half the distance, and then another half the distance, and then another half of the distance, and you never quite get to the wall because each time you're just going half of the remaining distance. That situation is analogous to this, where if we said we want to go all the way to the normal depth, this curve is going to be very infinitesimally still curved, but if we say within 1%, then it's essentially the normal depth, but we don't run into the problem of it being an infinitely long distance. Okay, so just as a reminder, when we analyze the critical depth for a rectangular channel, we can use this easy approximation, the critical depth 0.776 meters, solving Manning's equation with this channel geometry being rectangular, the slope, the n value, we get the normal depth. So within 1% of the normal depth, we're saying we want to know how far do we have to go upstream from this weir until the depth matches back up to 1.207 meters. So those are the two things that we're going to try to be solving. Now the slope that's given, 0.0015, we kind of have to manually calculate what are our elevations going to be. And if we say, let's have the bottom of the channel be our elevation datum just upstream of this weir, so z equals 0 by our definition. We could have called it 10, we could have called it 100. Let's just call it 0. Then if we go 3,000 meters upstream, that tells us that the channel bottom should be 4.5 meters as elevation. And that's just multiplying this 0.0015. That's 0.0015 meters of elevation for every meter of horizontal length that we're moving upstream. So if we're moving 3,000, the delta z is 4.5. Okay, so is everybody with me so far on what the geometry of the channel looks like? Everybody understand what we're trying to figure out with HEC-RAS? We could have done this, and we still could, using the spreadsheet. But the advantage of HEC-RAS is that it would, after we move past this simpler example, it allows you to handle when the channel geometry is changing between segments. So we'll take a look at this easy example to begin with, and then that maybe would inform what it's doing behind the scenes, like how it works in the background. All right, so look at these coordinates that now have just popped up for our channel. So we're going to have to define the upper left, the lower right, and the upper right. So we have to tell HEC-RAS what this channel looks like, and then we also have to tell it where is the bank. And our example, the bank and the edge of the channel are going to be the same, but if we have like a more sophisticated or complex geometry, it could be that you have something that looks like this. And so I'm just drawing on the board where we have a main defined channel. And so, you know, these are the points that would be defining the main channel. But then there's some flood bank. And so you're maybe wanting to extend beyond that to say, you know, if there's really extensive flooding, how far to the sides does it go? And so that might be that channel bank defined by a hillside in some places, or it could be a roadway. But in our case, we're going to kind of repeat this 0,4 location because that's going to be the edge of our channel and the edge of the bank. And the same thing here at 7,4. So it's an XY coordinate system that we're going to be putting into the program. Any questions so far? All right. Well, let's start up the program. I'm not sure if it's installed here on this machine, so I'll probably have to, oh, it is, good. I was going to remote into my desktop, but this is even better. Autodesk Inventor. Not sure why it thinks that's what we want. Maybe I will remote into my machine. All right. All right. So this is the let's start from scratch. New project. and we'll give it a name. You put it in a directory that you're going to be able to find again, and my suggestion is to create a separate folder. You know, don't just put it on your desktop, because it's going to create several different files as we go through the process of creating geometry and doing a steady state run. So create a subfolder here with this button. I'm going to go into my temporary folder, and I'll call this 331-RAS, and create that folder. And then I'm going to call it Tuesday Demo. All right. Now it looks like the units are, it just gave me a warning that my unit system is US customary. Oh, no, system international. Okay, that's what I want. But in your case, and down here at the bottom, it's confirming what units we're in. By default, I think it probably comes up in the US customary units, and so you're going to need to go to Options, and then Unit System, and switch it from US customary to System International. Okay. I'm going to set that as the default. Okay, so does everybody have the unit set so far?
It said title. What's the file name? It's giving me a title and file name that's specified.
You just type in whatever you like. So File, New Project, and then just type in here the title. And then I called mine Tuesday Demo. You don't have to call it that. But once you click OK, all right, so the first thing we're going to do is we're going to click here on this icon, View/Edit Geometric Data. So it's just right by the disk symbol. You guys probably don't even know what a disk is. This rectangular symbol that you've never seen in person before, a disk. Click on this one, View, Edit Geometric Data, and so what we have to do is we have to, from a top view, draw our river. And so this river reach button, add a new reach. Now be really careful because there's a specific thing that we want to do. And the thing we want to do is click once to start, move the mouse to the side a little bit, and then double click to finish. All right, so click on river reach. And so this is a top view. I'm just the start of my river, I'm moving over sideways. It doesn't matter if it's low or if it's high. This is just like a schematic diagram. It's not implying any particular length, but double click at the end. All right, and by double clicking, that means that we're terminating this river. And I'm going to call this river example, and the reach is going to be reach 1. Now, you can have multiple reaches on a river, meaning that, for instance, there may be side channels that are going up some particular holler, but they're all a part of the same river system. All right, so it's got a name, and you can see that it's put it in that top view, and the direction of the river is implied by where I clicked first and where I clicked second. All right, so next what we want to do is we want to create some cross sections. And so we're going to add a new cross section. So here, under cross sections, edit and or create cross sections. Click on that. And then here's the box that we're going to have to enter in the XY coordinate data. We're going to start with this location 3,000 meters upstream. Just to refresh your memory, I think that we might be able to create one model that answers both questions, because we're essentially trying to figure out how far of a length till it gets to 1.07 meters. And so if I create this entire segment of 3,000, I suspect that this unknown length is going to be within that 3,000 meter distance. And then the other thing I want to know is what's going on at 1,500 meters. So I'm starting at the upstream location. So let's put in the coordinates. Now, the upstream location, the geometry of it looks a little bit different. This is our downstream section, the x and y coordinates for the downstream. But the upstream, because the z is 4.5, then that means that this top left is going to be 0, 8.5. The bottom left is 0, 4.5. So this is x and y coordinates. 7, 4.5, and 7, 8.5. So those are the coordinates of the upstream reach. This spot where the z is 4.5 meters. Okay, so I'm going to start with 0. Okay, what have I forgotten here? Oh, I guess I didn't create it yet. So options, add a new cross-section. And it asks you to say what's the station. And so that means how far upstream or downstream is it? So again, what I did here, we're on the cross-section data, options, add a new cross-section. Okay? And we're going to put this in at 3,000. So that station is essentially, it means it's 3,000 meters upstream of where we've measured the depth. So at station 3,000, and so now it's naming that station 3,000. Now hopefully we'll be able to type in the coordinates, the x and the y. So 0 is the station. Now the station that this is talking about is it's measuring the cross-section starting at the left side. So there's the stations that run along the length of the river, and then there's the stations that are going side to side to define the channel geometry. So this station is just saying how far from the left edge of the channel are different features. And so 8.5 is that elevation. And also at 0 is elevation 4.5. Then at station 7, 4.5, 7, 8.5. So why 8.5? Well, remember that what we've said is that this is basically like a trough, a 4-meter tall trough that is going upstream. And so if we have the z is 4.5 meters and another 4 on top of that, it means the top of the channel will be at 8.5. Okay. Now this is saying the downstream reach length. From here to go all the way to that weir is 3,000 meters. So type in 3,000. Later on we're going to interpolate and it will break that up into smaller pieces. But for now we'll have it be 3,000. The end value for the left side, the main channel, and the right side, where it's saying LOB and ROB, that means the left of the bank and the right of the bank. And so you can define a separate end value for the floodplain if you've got that information. But in our case, we're really only analyzing what's going on in the main channel. So I'm just going to call the same Mannings of 0.02 for every place we need to define the roughness. Okay, and then we also need to tell it where is the left bank and the right bank, like the edge of the banks. And so it's just going to be 0 for the left and 4.5 for the right. And now that we've got all this typed in, if you click on Apply Data, it's going to graph that in this window on the right. What I do wrong? Oh, yeah. So 0, 8.5, 0, 4.5. This one is extraneous. I'm going to delete that. I'm not sure how that even got in there. All right, let's apply now. Something's still not quite right. That's exactly right. Yes, because the channel is 7 meters wide, right? Yeah. Okay. Thanks for catching that. There we go. Yeah. So these red dots, long story short, these red dots should be, for us, right at the edge, the same as what we're defining it. So you can see this horizontal line is representing the ground surface. So it's at 4.5 where it ought to be. And then what we're saying is you can see this line goes up to 8.5, and so that's the rectangular shape of our channel. All right, so we've defined the upstream section. And now what we want to do is we want to add a new cross-section at 0. So we've created this section at 3,000. Let's do options, add a new cross-section, and we're going to do it at station 0. Okay? And so it enters this new river station name, and we have to type in the coordinates again. So this top left edge, 0, 4, bottom left, 0, 0, bottom right, 7, 0, and 7, 4. All right. We'll enter in downstream. Actually, I'm not even sure if you have to, because we're not doing anything downstream of this particular section. Remember that this section is going to be at our control point. So I'm just going to experiment with leaving this blank because there isn't going to be anything downstream. The end values have already copied over, which is good. And then the left bank is at 0. The right bank is at 7. And we click Apply Data. And the bottom of the channel is down at 0. So it's at our elevation datum. The top goes up to 4 on both sides. So what we have right now is 2 stations, and we can toggle between them using these arrows. We've just got these 2 segments. But the nice thing that the program will allow us to do is it can interpolate linearly between these 2 sections. So, you know, if I wanted to break it up into, well, what would make sense based on where we want to know things. If we do it in 300-meter segments, so if I wanted to break it into 10 segments, then I could type it in manually a bunch and have to continue calculating what's the delta z and all that. Or we can just see about interpolating it automatically. All right, so under Tools, now let's see, I think what I do is close this window. Tools, cross-section interpolation, and we're going to do it between 2 cross-sections. Okay. So it'll bring that up, and the upper station is at 3,000. The lower station is at 0, so it knows which 2 stations it's going to be interpolating between, and it reports back that it's 3,000 meters between them. And then let's have it be a constant distance of 300 meters. Just to see what happens. All right, and then click Interpolate New Cross Sections. All right, so it looks like what we're seeing here is a front view of all of those different cross sections, and so we can see that the initial depth is down here at 0. Then, well, we can close that and investigate each of these sections together. So if we bring up the cross sections menu again, then we can flip between them. So if we go starting at the 3,000 now, 2,700, 2,400, and so check the elevations, and so we're at 4.5, 4.05. So what it's done, and you can see in this window, it's continuing to highlight the cross-section that you're on as we go down, and it's rescaling this view on the side, but it's measured all of these reach lengths, and and then we get to the end. We get to 0. All right, so it seems like it did what we would want it to do in interpolating those. And so we can close this, and then maybe it's a good time to save. File, save geometry. So I'm going to call this demo geo. All right, so now I've saved the geometry. All right, let's take a look if we close this geometric data. This is still open, so let's save everything. Click the disk symbol, save everything, and now it tells us we've got a project, we've got geometry. What we haven't told it anything about yet, though, is we haven't told it about the 15 cubic meters per second, and we haven't told it what the water depth is at that location where we know it. Remember, at this control point where we've measured the depth and it's known to be 3.8 meters, well, HEC-RAS doesn't know about that yet. So let's give it that information. So here is view/edit steady flow data. So the Q is constant. That's, I guess, a symbol for steady flow, whereas here it's unsteady flow because the flow rate is going up and then it's going down again. So we're going to do steady flow. Click on that. And let's set PF1 to 15 cubic meters per second. So see down at the bottom, it'll give you hints on what it is we're entering here. Edit steady flow data for the profiles. And so the water surface profile, we want it to do a graph of what's happening at 15 cubic meters per second. If we wanted to, we could add in other flow rates and it could analyze them in the same model so that we could flip between, show me what does the water surface look like at 15 cubic meters per second, at 20, 25. So we could add additional rows to this, but we're just going to analyze it at the single 15 cubic meters per second. All right, now we also need to set a boundary condition. So here under Reach Boundary Condition, click on that, and we have a few different options. There's different things that you can tell that are governing. And in our case, what we want to have it do is start with a known water surface. So it's this downstream known water surface. When the flow rate is 15 cubic meters per second, then the known water surface elevation is 3.8 meters. So 3.8, and it's asking as an elevation above the datum. It's not just asking about the depth, and so it's kind of just fortunate for us that we said that our datum is going to be at the bottom of the channel at that downstream section. You know in the homework how you had to keep track of a separate depth versus water surface elevation? Here they're one and the same. Okay, so click OK, and now it says that what's governing this boundary condition is the known water surface elevation that we've just set. Okay, so we can click OK and click Apply. I think it automatically applies, but let's click Apply just in case. All right, so everything's set. Save flow data. Example flow. Okay, so now if I want to open this up in the future, it would already have the project defined, which is that top view of my system of rivers and reaches. It would have the geometry defined and then our steady flow conditions. So now what we're going to do is perform the steady flow simulation. These icons are the greatest. See the guy that's running on a flat line? So that's a steady flow run. I guess he's running. So we're going to run the model steady. So click on that, and we have subcritical flow regime. And how do we know that? Well, because we calculate the critical depth is less than the normal depth. Okay, so subcritical is correct. It knows the right geometry file. It's got the correct input for the steady flow file. So in other words, it's sending this water through this channel. And click compute. Hopefully no error messages. Seems good. All right. So now what we can do, close this, and let's take a look at the cross sections again. With any luck, what we'll see is that there's water in those cross sections. There it is. There's water in those cross sections. So here we are at River Station 1200. Let's go down to 0. So is the water depth at 0 what we told it to be? 3.7? Yeah, it looks like it does have that 3.7. But as we work our way upstream, for instance, we wanted to find out what's happening at 1500, right? That was one of the questions in this example is, what is the water depth at 1500? Okay. Well, we can see from this graph that the water depth looks like it's about 4 meters of elevation is the water surface elevation there. And then what we would do is subtract out the bottom of the channel. So the actual water depth would be 4 minus 2.25. So it's about 1.75 meters. In just a bit, we'll take a look at copying this data and pasting it into a table. But you know, if we're just kind of visualizing things through the cross-section, the depth of the water is from the bottom of the channel up to the end of the blue. All right, so it was 3.8, and now it's down to 1.75 about. So it's definitely getting shallower as we move upstream, which is what we expect. You know, remember that we expect that it's eventually going to match in with the normal depth, 1.2. So it's a good way, you know, like it's getting close already. It's at 1.75 here at 1,500 meters upstream. So the question is, how many segments do we have to go until we see this depth of 1.2? So if we move upstream again, now we're at 1,800 meters. It's getting a little trickier. I wish there was some easy way to dimension the depth on this cross-section. I mean, there probably is a way. It's just that I don't know it. We will take a look at the table in just a moment. But as we keep working upstream, what we see is that the water depth is getting shallower. Eventually, we get to this 3,000. And so let's take a look at getting the view table. And so here under tables, no, actually, I don't think it's there. We're going to close this. So back here in the main menu, yeah, we've got a summary output table by profile, and we can also do it one cross-section at a time. So if we go back to that 1,500, which is a point of interest for us, it'll tell us the exact water surface elevation at that point. It's telling us it doesn't give us the channel, oh, there it is, the minimum channel elevation, 2.25. So the depth would be the water surface minus this minimum channel elevation. Though it doesn't look like they've done that. Oh, wait, hydraulic depth, there it is, 1.77 meters. Okay. So the depth is 1.77 meters at that halfway. So then let's move upstream, because what are we looking at? We want to see we're within 1% of the normal depth, so 1.207. Okay, so if I go upstream again, and I'm keeping an eye on this one, are we at 1.207 yet at 1,800? No, the hydraulic depth is now at 1.48. We're looking for 1.2. Okay, 1.29. We're getting pretty close at the 2,100. 1.22. It's giving us a warning here that the energy loss was greater than a foot. This may indicate the need for additional cross-sections. Well, lucky for us, that's actually pretty easy to do, to throw in more cross-sections. I could have made it 100-meter spacing instead of 300-meter spacing. So maybe we could go back and modify that. 1.20. So we're back to the normal depth by somewhere between 2400, and 2700. So if I needed more resolution, then what I'd do is I'd focus in on adding additional cross-sections between those two sections, because that's where it goes from 1.22 meters of depth to 1.20. All right, so any questions about this so far? Here's what yeah, go ahead.
Can you make that show 3 decimal places?
Boy. I tell you what, you're asking the wrong guy questions like that. I'm pretty ignorant when it comes to the full capabilities of this program, but I think probably what we could do, though, is export the table. And I don't know if we could do that just by viewing, but here is tables that can be copied to the clipboard or written to a text file. Let's see if we write it to a text file and then open that up with Excel, how much precision it gives us, because that's an interesting question. All right, so I'm going to call this one class demo.txt, and then if I open up Excel, let me open up that class demo text file, and we'll just take a look at what's in there. So we're getting the import wizard here. I'm not sure how this is delimited. Maybe spaces? Yeah, might as well. No, it's not giving us a tremendous amount of precision here. Like if the main thing we want to know is the elevation, yeah, that's an interesting question. Let me ask some of the people I know who are a little bit better at the program, because I'd be curious to know if we can get a greater degree of precision. All right, here's what I'd like to do. I would like you to try solving another one of these problems that we've worked in the past using HEC-RAS, and it is the one where it transitions from a trapezoidal channel to a rectangular channel. So let me bring that up. Let's try and adapt this example. So it's in traditional units. We've got an n value. We've got an expansion coefficient defined. So in this one, we had a the water depth was known to be 5 feet at section 1, and then we were working upstream towards this, to this rectangular. And the cool thing is HEC-RAS is going to be able to gradually open up that transition. So we aren't just going to be doing it in a single step. It's like immediately going from rectangular to trapezoidal. So my suggestion is let's do a 1,000 foot between them. So define this downstream section 1, define the upstream section 2, and of course the station will be 0 for section 1, station will be 1,000 for section 2, and then have it interpolate in increments of 100 feet. And then let's find out basically what's the water depth doing at each of those locations, and the location that we're most interested in is going to be at section 2, where we want to find out what is the water depth there. All right, so the time is yours. I'm going to try and solve it as well, and we'll see if we're all on the same page. We've got about 25 minutes that we can work on this one, so that I think should be plenty of time. kind of exaggerates the vertical distance on that trapezoidal channel. So the known is this known water depth is 5 feet at section 1. And so we're working upstream. We want to know how deep the water is going to be there.
So whenever I switched it back over to custom reading, just for the sake of trying, it looks like everything remained the same as far as the
Coordinates?
Yeah.
All right. Cool. Okay, so after you interpolate your cross sections, and here's my starting cross section. I had 0, so 0, 10, 10, 5, 35, 5, 45, 10. That defines the trapezoid. Okay, and then the other one that was defined was the 1,000. So just to go back here, 0, 10, 10, 5, 35, 5, 45, 10. That's the cross-section of the trapezoid. And then at 1,000, it was this rectangle, and I interpolated. And if you scroll through, you can see that gradually in the interpolation, what it's doing is it's becoming less trapezoidal and more rectangular until finally we get up to 1,000 and it's perfectly rectangular. Okay? So then what I want to do is I want to view edit steady flow data, and I have to put in the flow rate. So down here, edit steady flow data for the profiles, 1,000 CFS. So I have 1,000 CFS in the givens. And then I also want to take a look at the reach boundary conditions. And the boundary condition is that the downstream section, here at 0, it's known that the known water surface elevation is 10 feet. Now, does everybody understand why I said 10 feet is the water surface elevation? Because in the sketch, the problem, it says that the water depth is 5 and the invert is at 5, so we're measuring all of the elevations relative to that datum. Okay. So we've got a known elevation, we've got the flow rate defined here, 1,000. I think that this 1,000 is like how many calculations it'll do before it finishes. Yeah?
Does it matter if you select the river station right there too, even though you're on river station 1,000, we're talking about water surface
Here?
station 0, yeah. I didn't know if it's 0 there and then put your conditions.
Well, let's find out. I'm not sure. I think that the reach boundary conditions, because we've already told it that it's a downstream that we've got the known, I think that it's applying the depth to the most downstream section, but hopefully it doesn't throw things off because I had something else selected. It doesn't appear to change anything that I've entered depending on what's in that drop-down, but it's good that you're keeping an eye on the details like that. All right, so let me save that. Okay, so remember, the way we think about this, the geometry is the trough, the channel that the water is flowing down. The steady flow data defines the depth at one of the locations and how much water is flowing through. Now, this is just a mystery to me whether it's actually going to run, but I'm going to perform that steady flow. Subcritical conditions. Well, let's see what it says. The trick could be that it might not be deep enough upstream. I've made the channel 20 feet deep. Hopefully that's enough to hold the water. Let's see. If I pull up the cross sections, then that should give me an idea of what's going on with the water. So starting here at 0, what I want to see is I want to see the water depth of 5 meters. So feet, excuse me, from 5 to 10. So 5 feet deep. And then as I work upstream, it seems to have worked. Anybody want to guess what this, oh, I guess you don't have to guess, there's a legend. The dashed green line, it's the energy grade line. So, it's the depth plus the velocity head, so it's graphing the energy grade line. So if I want to know what is the water depth at that section where it goes back to rectangular, looks like, where was the place that it was convenient to look at those on an individual basis? This detail here. So 1,000 is where it's rectangular, and my hydraulic depth is 7.69 feet. I didn't bring my notes to see, like when we calculated this. I guess I could pull open the Excel file, but remember we did it in a single step. What was the depth in that example? Let me see if I can pull up the spreadsheet version of that one. It's going to be different because we divided it up into so many other sections. But standard set method. So in this one, it was converging to that section 2. It calculated the depth was 8.05. So HEC-RAS is saying 7.7, and you'd expect there to be some variation because all of these different rows, it doesn't represent multiple sections, remember. These are just different iterations. So it agrees well enough. I'm not too scandalized by the difference between the two, considering that we've broken this up into 10 segments where it's gradually opening up the sides. All right. I don't like hearing that question, so I'll just tell you this won't be on the test. It was just for your learning. So just for your edification, maybe someday you'll have an opportunity to use this, and if you do, it'll be installed on your laptop, and you'll know that you've got a recorded class video you can track down on YouTube where you work through a couple of examples. All right.
Free of charge.
Free of charge. Yeah, all you have to do is sit through a commercial. Yeah. All right, let's take a look at the announcement. They're not plural at this point, really. This one? No. All right, the handout problem and the book problem. This was related to sewer design. That's due on Thursday. Has everyone been receiving the hints that I email you? Whenever I get a particularly good question via email or by somebody stopping by my office, I try and pay it forward to everyone in class. So be sure and check your email. You may get a little nugget of truth to help you with the homework. So upload that before class on Thursday, and then on Thursday we'll just have one last lecture where we're going to be talking about, it'll be a surprise to both of us. I don't remember what's on the schedule for Thursday, but I will come prepared. I'll see you then.